I think the plan for this afternoon, we went to the botanical garden earlier, but we got there too late, so we're going to try to go again today. We're going to leave like after the last talk, give yourself 5 minutes to pack your backpack. There's a university bus that goes up there. I think it's a couple dollars if you're not with the university. It's pretty cheap.
But do you need to buy the tickets before? You can buy on the.
I think you should be able to buy them there. So the ticket price, if you have a ID, a UCB ID, it's free. If you're a student that's not a UCB student, it's $12. And if you're just a generic person, it's $18. And then it's like a half-hour walk back, or you can take the bus back, or you can take an Uber, however you want to get back. I presume most people will walk back.
Where do we meet?
I guess just out by the front door. I'll probably make an announcement at 3, so you have 10 minutes to, use the restroom. All right.
And now we're happy to have Jeremy Fineman give a talk on parallel algorithms for directed graphs.
Great, thanks. So we've seen a bunch of algorithms for undirected graphs already. I'm going to be talking about some of the techniques for directed graphs. You'll notice that I'm covering a bunch of algorithms. Many of these are either from the 90s or from the last 10 years. There's really not much in between. And feel free to ask questions as I'm going, because the more questions you ask, the less it looks like I prepared too long a talk, and I can blame it on you. All right, so let me just start. I'm really going to be talking about 2 types of problems, reachability and shortest paths, and then some related problems I'll put up on one slide. Throughout the talk, I'm going to be using n and m to talk about the number of vertices and the number of edges, respectively. I'll also be using this O tilde notation in the most sloppy form. So it's not the typical soft O. I'm using it to hide log n. It's always log n, even if there's no n in the function. So it's just syntactic sugar. That will allow me to write things like O tilde 1 to mean polylog. For parallelism, I'm generally thinking in the work span model, also called the work depth model. We don't actually really have to think about what the computation model is, because I'm ignoring log factors. So you can convert from pretty much any model to any other model with logarithmic overheads. So don't worry about that. In fact, the parallelism itself is going to be very high level when it comes down to it. I'm also only going to be looking at algorithms that work for general directed graphs. There are better algorithms if you're considering special cases like planar graphs. I'm not going to be talking about those at all. I'm also going to be thinking generally about worst case analyses. So again, there's probably better things if you're sort of considering other settings. OK, so the first problem I want to cover is the single source reachability problem. This is a problem I'm going to be talking about for most of the talk. So the idea here is we're given a directed graph. We have some source vertex like this one over here. And I want to figure out all the vertices that I can reach from a directed path starting at that vertex, which would be all the ones I've highlighted in orange in this picture. Sequentially, this is very easy to solve. You would just run any graph search, like breadth first search or depth first search, and you can do this in linear time. Okay, in parallel, it's a bit harder. The sort of easy parallel solution is to just simulate breadth first search in parallel, where you explore each frontier of the breadth first search in parallel, but you're still going to take a number of rounds or a number of iterations that's proportional to the number of hops in the breadth first search. So this is reasonably parallel if the graph is dense. It's also reasonably parallel if the graph has very low diameter, where the diameter is the length of the longest shortest path. But in general, if you have sparse low diameter graphs, you can't really argue that this does any better than just running breadth first search sequentially. So for instance, this would be a terrible graph for parallel breadth first search. Now this is a graph that we can do much better for. This is just a list. We can run list ranking and things like that. But if you have a graph that contains something that looks like this and some other edges, then I can't do list ranking or anything like that to speed this up. OK, so in this case, the worst case number of rounds would be the length of the path, which can be up to the number of vertices. OK, so the main approaches involve adding shortcuts either explicitly or implicitly. A shortcut is just an edge whose addition doesn't change the transitive closure. We're trying to solve reachability, so adding extra edges that don't change anything are totally fine. And there's sort of two points of view on how this should be done. The most common one is to observe that if the diameter of the graph is low, then parallel breadth-first search works pretty well. So let's just pre-process a graph, add a bunch of shortcuts to the graph, with the goal of making the diameter smaller. Once we have that, we can just run parallel breadth-first search. There is one other algorithm that fits into a different point of view. That is, if the frontier is always large, then parallel breadth-first search will also be kind of fast because you're discovering a bunch of vertices in each step of the algorithm. So let's instead add shortcuts on the fly with the goal of increasing the out degree of every vertex. And we'll sort of interleave that shortcutting process with the breadth-first search itself, so that every time we take a step in breadth-first search, we discover a bunch of vertices. So pretty much every algorithm except for one fits into this first point of view. The only algorithm I'm aware of that follows the second point of view is Spencer's algorithm, which is the one I will talk about next. I think it's pretty clever and pretty cool. It's been getting a little bit of attention recently, but I haven't seen any other algorithms that use the same kind of strategy. OK, so let me give you an idea of Spencer's algorithm. We have some parameter rho, which is going to control the out degree. And we're basically going to be running breadth-first search here. So we're going to start with the frontier. Breadth-first search is just the source vertex. And while the frontier is not empty, I'm going to add this extra step. You can do this explicitly or think of it just conceptually. I'm going to remove all the edges directed toward the frontier. So those would now S has no edges coming in. And now I want to add some shortcuts to increase the out degree of every vertex to at least rho, if possible. So the way you would do that is you would look at every vertex in parallel, look for the low degree vertices, and add shortcuts to your neighbor's neighbors. I'll give a little more detail on this in a moment. So maybe I add a bunch of shortcuts to like this. Now I decide that everybody has big enough out degree, so I will perform the next round of BFS. So I'll discover the frontier, remove the incoming edges. Some vertices got lower degree as a result. So we will again try to increase their out degree and repeat the process. OK, so that's the general strategy that Spencer's algorithm adopts. So let me give a little more detail for like a first crack at this algorithm. So what do I mean by low degree vertices add shortcuts to their neighbors' neighbors? We want this to be kind of efficient. So if I have a vertex over here, it has fewer than rho neighbors because it's low degree. And it has a bunch of neighbors, a bunch of vertices in the 2-op neighborhood. You might be able to reach some of them in multiple ways. I kind of don't want to add shortcuts to everything here because there could be an unbounded number of things, and that would take me a lot of work to add all those shortcuts. So I can stop once I see rho vertices on any high degree vertex. So I'm going to add shortcuts to rho of all my neighbors' neighbors. OK, so maybe I'll add those shortcuts to the graph. So if you do this correctly, this takes rho squared work per vertex, right? OK. And now we're sort of guaranteeing that every vertex has degree at least rho. So when we advance the next round of BFS, we are going to discover rho vertices. So that means that we only need n over rho rounds of BFS. So if we crunch all the numbers, we have n over rho rounds of BFS. These rounds are each very parallel, so you could do this in something like n over rho span. But in each round, each vertex has to do rho squared work. So when you multiply that out, you get n squared rho, which is a lot. Yeah.
You could just have like a low degree neighbor whose neighbors are low degree. I mean, you might not get up to rho. Right?
Oh yeah, that's why. I said you got to repeat this over and over.
Oh, you keep going. I see.
You repeat until everybody has high degree.
I see. Okay.
Yeah, so you got this sort of pointer jumping, doubling thing going on. So you won't need to repeat more than log n times before you've reached everything. Yeah, good question. Yeah, OK, so that's the sort of warm-up implementation. Yeah.
Sorry, why do you keep doing doubling after every round of the BFS?
Well, that's a good question. It's very wasteful, right? Yeah. So I think as a first crack, it's not obvious how to beat that. But Spencer's algorithm has a nice little trick to do that. So that's what I'm going to do on the next slide. Yeah, so the observation is that this is very wasteful. because we keep doing the doubling. We're kind of repeating some of the same work, but we do want to amp up the degree between each round because we don't know how degrees have fallen. So Spencer's algorithm to get an efficient implementation relaxes the, I think I present this differently, or I think of this differently from how it's presented in the paper and how most people think of it, but this is my viewpoint of it. So essentially, we're going to relax the out degree requirement. So rather than saying that everybody has to have out degree at least rho, we're going to say that we want it to be that every vertex has a high degree vertex within a short distance. You get almost the same effect. You're going to increase the number of rounds a little bit, but that's going to be our goal. And the way you can do that is as follows. We're going to give each vertex a rank. And rank R means that it already has shortcuts to everybody it can reach within 2 to the R hops. We're doing this doubling kind of strategy, so we're going to try to maintain this as we go. So the maximum distance you can be talking about is 2 to the log n, so the maximum rank is log n. And we're going to tweak that expansion, adding shortcuts to neighbors of neighbors algorithm to say we're not going to expand a vertex if one of these 2 conditions is hit. So one is if you have a neighbor without degree greater than rho, you're already done. There's a high degree vertex right there. Or if you have a neighbor with lower rank, you're not going to do the doubling either. Okay, so what can happen is you can end up with a vertex with rank R that has low degree, pointed at a vertex with strictly lower rank with low degree, and you get this sort of decreasing chain of ranks. This can have length at most log n, and would have to end at a high degree vertex. I'm not proving that, but hopefully that's believable. Okay, now if you have low degree and all your neighbors have the same rank, or higher, then what you can do is add shortcuts to your neighbor's neighbors. Now keep in mind that you had edges to everybody you can reach in 2 to the R hops. They had edges to everybody they can reach in 2 to the R hops. So your neighbor's neighbors are the things that you can reach in 2 to the R plus 1 hops. So now you can increase your rank by 1. Okay, so this is what Spencer's algorithm actually does. And the nice thing here is that each vertex only gets this neighbors of neighbors expansion log n times in total throughout the entire course of the algorithm. So the total work becomes n rho squared for this neighborhood expansion plus the m for the BFS itself. Okay, so I think that's a very cute trick. Nice, clever algorithm. This was one of my favorite parallel graph algorithms from back in the day. That's the way that works. Okay, now as I already pointed out, the number of rounds of BFS will increase when you're doing this because you no longer guarantee that in 1 hop you're going to get to a lot of vertices, but you know that it's going to happen within log n hops, so it doesn't change too much. So again, here's just a summary. The work we get is going to be n rho squared plus m. The span is n over rho. So if you plug in something like rho is square root of n, you get work n squared and span square root of n. Yeah.
If you use a fixed number of processors, it's like the higher the row is, the worse it is, right? Is that a good way of thinking about it?
Well, rho doesn't have to correspond to the number of processors.
No, but if you have a fixed number of processors, then if you increase row, the work increases by a rho squared factor, but you only you only save a row factor in the span.
Yeah, so you end up getting, I don't remember, you get speed up that's like square root of the number of processors, or I think it's actually cube root of the number of processors or something like that.
Is there actually a way to set it so that there is any speed up? I mean, it's
only if the graph is dense for this one. Okay. So you can set rho to be like square root of the average degree, and then this will be something that gives you. So yes, you will get speed up. The more processors you throw at this, it does speed up. It's just less and less efficient. So you got to plug the numbers in.
You do that by changing rho?
Yeah.
So you make the rho dependent on the number of processors?
Yeah, so you'd set rho to be something like the cube root of the number of processors or the square root of the number of processors, I don't remember which, and then this all works out. But you don't get as much speed up as you would want. Okay, so that's one strategy. I want to give another one. So the other strategy is to try to shortcut the graph to reduce the diameter. So here we have, let me just set up the problem again. I have a directed graph. I don't care about a source vertex anymore. And my goal is to add a set of shortcuts to the graph so that the augmented graph has diameter that's much smaller than n. So maybe add a bunch of shortcuts like that. And if I'm trying to solve the reachability problem, this means that after I shortcut, I would just run breadth first search from the source vertex. If you're doing like multi-source BFS, the advantage here is that you've already shortcutted. Once you've shortcutted once, you can run BFS over and over with different source vertices and not have to redo the shortcutting because the graph already has low diameter. So the work here is going to increase because we've added some edges to the graph. So we kind of care about how big this shortcut set is. So ideally, we'd like the shortcut set to not be much bigger than the size of the graph. And that's mostly the regime I'm going to be looking at. Okay. So are there good sequential shortcutting algorithms? Well, let me give you sort of the easy thing first. We're going to sample row vertices, maybe those yellow ones over there. Run graph searches from each vertex, or from each sample. So this is going to have a lot of work. We need to do graph search row times. And then I'm going to add shortcuts between samples if they can reach each other. So I'll get extra edges that look something like that. This will create at most row squared shortcuts, so that's good. And it's also not hard to see that the diameter will get smaller. It gets smaller by a factor of rho. And you can see that just by looking at a path in the graph. And if I focus on the beginning of the path, the first n over rho vertices are very likely to have a sample selected. And if I look at the end of the path, the last n over rho sample or vertices are likely to have a sample. And I'm drawing shortcuts between all pairs of samples, so I get to shortcut directly. And now I have this green path that does not very much at the beginning, not very much at the end, and one edge in between. Okay, now this is an expensive algorithm, right? It has work that's super linear, but very simple. It's also sequential. Okay, there is a parallel version of this algorithm. This is due to Ullman and Yanikakis. The main ideas are the same. We're going to sample row vertices and run a graph search from each sample. But instead of doing an arbitrary graph search, we're going to use a parallel breadth first search. And we're going to limit the number of hops that we need to go, which is going to allow us to bound the span. So we're going to limit it to n over rho hops, where n over rho is the diameter we're trying to reach. So in this case, I'll add 2 of the same shortcuts, but I might not add this third one because those vertices are too far apart. I think the path, the way I've drawn this, has to go up around this way to get down to that vertex. Okay, now you can't do exactly the same analysis, but it's pretty similar. If I look at a path, I now need to chop. I can't argue that there's a shortcut from this first vertex to this last one because they're very far apart. But I can just chop the path into segments of length roughly n over rho. There has to be a sample in every segment. And then I'll shortcut to consecutive segments. So now the length of the path is a bit longer. It's n over rho plus rho, which is the number of segments I have. So if you have rho less than square root of n, then this gives you m rho work, n over rho span, and n over rho diameter. Okay, so pretty simple strategy. There's some details to get this right, but it's not too hard if you don't care about log factors. I think Ullman and Yanikakis did care about log factors, so they did a little bit of extra work in there. Okay. Now, they do describe how to do this algorithm when rho is very big, which means that the number of segments will be quite large, and this path is still much larger than our target diameter. So roughly speaking, you just run a different algorithm on the graph over the samples. And they, at some point, run matrix multiply in there. So when you put everything together, you get this work in this span. This rho to the 4th over n is roughly coming from matrix multiply on row things, row by row matrix. And again, if we're interested in the linear shortcut case, we would set rho equal to square root of n, which would give us m root n work and square root of n span. This algorithm is never work efficient because we're always going to have rho overhead. So you'd have to compare this versus the n squared you would get for Spencer's for the same diameter. If the graph is sparse, this is better. If the graph is dense, Spencer's better. OK, so what about other algorithms? Well, let's just think in the sequential case for now. I showed you the sort of simple sampling approach that would add n shortcuts, give us a diameter of square root of n, and have this very high running time. And you can make that parallel using the Ullmann-Yannikakis approach. And for a long time, that was sort of the only linear size shortcutting solution that was known. In 2018, I gave an algorithm that shortens the diameter to a little worse. It's n to the 2/3. But we can do it in linear time. So this is much more desirable. And you can make this parallel. And then a year later, Djembalupati, Liu, and Sidford showed how to improve the diameter that you get from this algorithm to roughly root n. And that can also be made parallel. And then very recently, it's been shown that you can actually get the diameter even smaller, down to n to the 1/3. But we don't have an efficient algorithm for that yet. And we don't know how to do that in parallel yet. So that's sort of the state of the world as far as sequential shortcutting goes. There are lower bounds on shortcutting. So if Bodwin and there's a long sequence of results here. I'm just sort of showing the best one. Bodwin and Hoppenworth showed that if you're limiting yourself to n shortcuts, the best diameter you can hope to achieve is n to the 1/4. So you cannot get polylogarithmic. You definitely need some polynomial in there. And Vasilevska, Williams, Shu, and Shu showed that if you are allowing linear in the number of edges shortcuts, you can't beat a diameter of n to the 1/5. Okay. I'm going to give a little, actually, a bunch more detail on my shortcutting algorithm. Yeah.
So I suppose those bounds, they talk about adding edges, but you could also imagine adding other structures, like adding some auxiliary vertices. Do those bounds rule out those cases, or is that not captured?
I think those are not captured. So there's like there are some lower bounds that say that adding vertices don't help if you're trying to like shortcut to 2 hops or something like that. But I don't think it's known whether adding extra vertices does anything. It's not clear how it would help, but yeah.
So those lower bounds are really sort of, there exists a family of graphs for which no matter what shortcuts you do.
That's right. So the question is about the lower bounds. The lower bounds construct a family of graphs, and they show that it's impossible to give every pair of vertices a low distance without adding too much shortcuts to the graph. Yeah.
Actually, follow-up question on that. For that particular family of graphs, is it also somehow fundamentally a difficult class of graphs? Like if I designed a special parallel algorithm just for that class of graphs, would I do something completely different?
So the question is if that family of graphs is inherently difficult, and I don't remember.
Gotcha.
I can't answer that. I would say that the lower bound for these two algorithms is actually a very easy planar graph for which you have much better algorithms. So it's a little bit strange, but yeah.
So just to be sure, the lower bound is existential one. It's not computational one. I mean, there is no computation issue here.
They don't care about computation at all, yeah. So this is just, it is impossible, however you want to do it. If you add fewer than n shortcuts, there will be a pair of vertices that's too far apart. Now, these are probably things that don't really appear naturally, but you'd have to dive into them. All right, so let me give you my algorithm. This is I'd say this is probably, if you think about the problem, the most natural divide and conquer solution for this problem. The question really is just, does it work well? So what we're going to do is we're going to choose a random pivot vertex. So let's say that green vertex up in the middle. I'm going to run a graph search forwards and backwards from that vertex. I'm describing this in the sequential setting for now. I'm going to run a graph search forwards and backwards from that vertex to figure out everything I can reach and everything that can reach me. So these are the things that you can reach in the forward direction in the graph. These are the things you can reach by going backwards along all the edges. And then we're going to add shortcuts from all the things in the backward set to x, and from x to all the things in the forward set. Okay, good so far? Okay, so now we're going to partition this graph depending on which of the searches reach these things. So we have 4 subgraphs, but I've only drawn 3 up here. We have the things that aren't reached by either graph search. We have the things that are reached only in the forward direction, the things that are reached only in the backwards direction. And then there's the things I've left out, which are the things that are reached in both directions. We can drop those because that's a strongly connected component that we have found. And everything in that strongly connected component is connected by 2 hops through x. So we can just kill those. So we're just going to recurse on everything else. And that's the algorithm. Okay. We want to understand how this algorithm works. So we kind of have to show 2 things. One is a diameter bound. So I can argue that with constant probability, if you look at the shortcuts you've added, the distance between a particular pair of vertices is reduced to n to the 2/3. You can also show that the running time is roughly linear. And then just to boost this into a high probability result, you repeat a bunch of times, and that gives you the main theorem below. I'm not going to talk about the running time bound at all. The algorithm has a very quicksort-like structure, so it should not be surprising that you get a quicksort-like bound. In fact, this is the same recursive structure as a divide and conquer algorithm for topological sort and strongly connected components due to Coppersmith, Fleischer, Hendrickson, and Pinar. And they already showed that that runs in linear time. The only difference between this algorithm and theirs is that they don't add shortcuts. So we're just doing that. That doesn't really increase the work. So I want to give a little idea about how we would argue that the distance goes down. And to do this analysis, we're going to fix a path that we're talking about, like this pink path over here running along the bottom. Okay, and what I'm going to try to reason about this in maybe a counterintuitive way, but I'm going to think about what happens to this path as the algorithm executes. The algorithm doesn't know the path. I'm not changing the algorithm. I'm just only going to zoom in on what's important to this path itself. Okay, and there's a few cases for what kind of pivot I choose. So one option is I choose a pivot like this one over here, and none of the path is contained in either the forward or the backward search. So I would say this pivot is unrelated to the path. So in this case, the entire path goes to the unrelated subproblem. We didn't get any useful shortcuts because there are no shortcuts between the path itself. But nothing bad happened. The entire path is still all together, so we're just going to hope to shortcut it when we recurse. Okay, so we're going to just ignore this case. It doesn't matter. The second case is the good case. We choose a pivot that has the sum of the path in the backward search and sum of the path in the forward search. So I'd say this pivot is a bridge of the path. And this case is great because we're going to add a shortcut from the start of the path to the pivot and from the pivot to the end of the path. So now we've gotten things down to 2 hops. Okay, this is what we want to happen. And at this point, the algorithm will continue to recurse, but we don't care about what happens anymore because we're already done. So this is sort of the base case as far as the path is concerned.
You need the source to be in the back end.
Yeah, so you would apply the same reasoning to subpaths later as well.
I see.
Yeah, so it wouldn't be the absolute S and the absolute T. It would be the beginning and end. Yeah. Yeah. So then there's 2 symmetric cases. So if some of the path is in the forward search, but none of it is in the backward search, I would call that pivot an ancestor of the path. And in this case, I'm not drawing the shortcuts in because none of them are useful for us, or at least I can't argue that they're useful. And what happens here is some of the path ends up in the forward search, and some of it is unrelated to the pivot, so the path is split across 2 subproblems. Okay, now maybe counterintuitively, splitting the path across subproblems is bad. We kind of think about splitting things and divide and conquer as being good, but here I'm trying to draw shortcuts. So I am never going to be able to shortcut from the left half to the right half again because they're entirely different problems. Okay, so this is bad. We want to sort of argue this doesn't happen too much. Yeah, and to answer, or with your question, The S and T I'm talking about would now be the beginning and the end of the path when I recurse, or the subpath when I recurse. And there's a symmetric case for a descendant, which is something that can be reached by the path, but not the other direction. Okay, so how do we argue that these bad cases are making any progress? And the trick is to focus on the total number of ancestors and descendants that are related to the path and its current subproblem. So in this example, all of these green nodes are currently ancestors of the path, and this blue node over here is a descendant. So there's 11 ancestors and descendants. We choose a random pivot like X over here. This partitions the graph. And if we look at least on this example, some of those ancestors are still ancestors in the forward subproblem. In fact, the descendant is still a descendant in the forward subproblem. Some of the ancestors went into the unrelated subproblem, but they're no longer related to the subpath that lives there. So they're no longer ancestors once we recurse. So like this guy and this guy are no longer related to the subpath in their problem. And some of the ancestors went into the backward subproblem, and so they're not in a problem that contains the path at all either. So if you count all of this up, in total we went down to 6 ancestors and descendants. That's roughly a constant factor reduction. And we'd like to argue that you get this most of the time. Okay, so if you're knocking out more and more of the ancestors and descendants as you go, eventually you can't really choose them anymore because there aren't any left, and you're going to be very likely to select vertices that are bridges, but really specifically vertices that are on the path itself that are automatically going to shortcut the rest of the way. Okay, so the question is sort of how bad this effect is going to be and what the diameter you get as a result is. Do you have a question, Kubash? No, okay. Okay, so this knockout argument is kind of cute, so, and I can do it by picture, so I'm going to do that as well. So let's focus on just the ancestors. I think one of the tricks here is you have to realize that you have to focus only on the vertices on one side, so either ancestors or descendants. But I'm going to look at 2 ancestor vertices. So these are vertices that have a way to reach the path, but there's no way to get from the path to these vertices. And we have 2 cases. So the first case is that these 2 ancestors are related to each other in some way. So I'll make X the one that can reach Y. Okay. So let's suppose that we chose Y as the pivot. We would do this sort of partition. X would end up in the backward subproblem. None of the path would be related, or would be in the backward subproblem. So X is no longer an ancestor once we do this partition. So I would say that X is knocked out. Okay, so that's one case. The other case is that X and Y are not related to each other. So that would be a picture that looks like this. And importantly, I'm drawing this edge over here to the earliest point that Y can reach on this path. Now let's suppose we chose X as a pivot, and we get a situation that looks like this. You'll see that Y and X are unrelated, so Y is in the unrelated subproblem. There is some of the path that's in the unrelated subproblem, but that path comes before the earliest point that Y can reach, so I know there's no way from Y to here, so Y is no longer an ancestor. Okay, so a very simple argument. We have this nice, so in this case, Y would be knocked out. We have this nice argument that one of the 2 vertices is going to knock the other one out if you choose it as a pivot. So if you choose a random ancestor as pivot, in expectation, you knock out half the ancestors. Okay, so this is a very simple argument. I think once I noticed this is when I was able to sort of push through the rest of the algorithm.
If in like the second case, X was chosen as the pivot, is Y knocked out?
If X is chosen as the pivot, then Y is knocked out in this case.
So
Yeah. If Y is chosen as the pivot, then it's not.
Oh, sorry, that's what I meant to ask, right? So if Y is chosen, so you're saying is...
So if Y is chosen as the pivot, then X would be in the unrelated subproblem, as would all of this stuff over here. So X would still be able to get to the piece of the path that's in its subproblem.
But you don't knock out.
I see, and X with half the answer. I see. So
Yeah.
Oh,
So you can think of this knockout thing as a complete graph where the edges are directed in at least one direction. So if you choose an expectation, you're going to have at least half of the edges are outward. So you're going to knock out half the.
I see, okay.
Okay, so you can argue that once you've chopped the path into the 2/3 pieces, there really aren't enough ancestors or descendants left to do much more. So you get a diameter of n to the 2/3. There's some details there which I'm just skipping, but that's basically the point. We have constant factor progress, so we can do something. Okay, so how do we make this parallel? Well, here's the algorithm again. The problem was we had these two steps where we need to do a graph search. Right, and we need to parallel graph search in order to do this in parallel. So obviously, the way you're going to attack that is to use parallel BFS limited to some number of hops, because that's sort of the only tool we have to do reachability in parallel. But then this messes up a lot of the arguments I just gave you, because we no longer have transitivity when we start truncating the graph search at a particular point. So the details get quite tricky to make this work. Okay, now fortunately, in the future, Heupler, Zhang, and Saranarek had this nice reduction that I'll describe in this slide. This will be in SOSA next year. So they say, so let me set this up. So we're going to look at a shortcutting algorithm with a target diameter d, so like n to the 2/3. And we'll pretend that we're going to focus on the case that the input graph is shallow. So its diameter is not much more than the target diameter that we're trying to hit. If that's the setting we're in, if we know the input graph is shallow, we don't have to worry about doing a hop-limited breadth first search. If we run breadth first search all the way, it's just automatically going to finish quickly, right? So the previous algorithm is just parallel. I don't have to do anything. So this theorem says if the algorithm's correct on shallow graphs, then there's a black box reduction that makes it so it works on graphs that are not shallow. Okay, so this means I don't have to do all the cruft that I did to make it work in my previous paper, which was like twice as long as the sequential algorithm to do the parallel algorithm, with no interesting parallel techniques, just dealing with the fact that you're truncating the breadth first search. Okay, so I'll give you an idea of how this works on the next couple of slides. Yeah.
Sorry, so the result here is if we have a shortcutting algorithm for a shallow graph, this gives you a shortcutting algorithm for any graph, right?
Yes.
Okay.
Yeah, this is an informal statement of that, but yeah, that's what it says. Okay, so what we're going to do is we're going to do something roughly as follows. So let me skip the first step, and let's just pretend that the graph is acyclic and we were given a topological sort of the graph. We don't have this, so we're going to have to fix that in a minute. And then we're going to consider breaking up the graph into subgraphs of consecutive vertices. So let's imagine that we have this subgraph already has low diameter, and this subgraph already has low diameter. Then we're going to try to merge these together into a larger subgraph and argue that we can make this have low diameter. Okay? Now, the only thing we need to observe is that, well, this has this is shallow. This is shallow. If we look at any path in this combined graph, if it's fully contained in one of those two things, it's already short. If it crosses those two things, it can only cross once because we have a topological sort. So it can only be twice as long as our inputs. So this is still shallow. So we can now run our shortcutting algorithm that works for shallow graphs. And we can make the diameter of this green graph at most d. And you can just keep doing this merging, log n rounds of sort of doubling this way. And you've managed to apply the shallow graph algorithm to work in general. Okay. Okay, now the issue is we don't have that topological sort. So we're going to rely on a tool that's relatively recent called a low diameter decomposition. These have existed for undirected graphs for ages, but there's directed versions that have come into use. These are used, for instance, in that breakthrough linear time integer weight shortest path algorithm from a couple years ago. Let me just give you the idea of what these do. I'm not going to tell you how to build the low diameter decomposition, but roughly we're going to approximately topologically sort the graph. So in slightly more detail, the algorithm is going to be allowed to remove some edges. Those are the ones that are marked in red. And then subject to whatever it removes, so we look at the remaining graph, which is the edges in black, it will find the strongly connected components of that remaining graph. So those are each circled here. And it will produce a topological sort of those strongly connected components. And each of those strongly connected components will have low diameter. So that's all the low diameter decomposition does. Okay, now you notice that almost the entire graph isn't a strongly connected component if I include the red edges, but the algorithm was allowed to ignore those. Okay, it gets to choose which edges it's ignoring. It does this with a bunch of like ball growing type things. Okay, so you can do this efficiently, and I'm just going to skip how to do that. But does the problem it's doing make sense to people? All right, so now let's go back to our original problem of generalizing this approach. And it turns out you don't need to worry about shortcutting long paths down to diameter d. We only need to worry about shortcutting a path of length 2d down to d. And then you could just reason about cutting your long path into subpaths of length 2d and keep having the length of your full path by doing this. Okay. So what we're going to do is we're going to find a low diameter decomposition where the diameter we're using is something like d, the target diameter of the shortcutting algorithm. And then we're going to apply the simple strategy that I presented for the topological sort assumption. That works here, even though I have strongly connected components. These are all low diameter by assumption, so it works OK. We can do exactly that strategy. So if all we had were the black edges, we're already done. So the only issue is that we might have some relationships that can only be gleaned by looking at the red edges as well. So we just need to reason about paths that involve red edges. Well, nicely, these are not, we're not concerned about paths that are very long. I only care about paths of length 2d. And each edge is unlikely to be cut by the low diameter decomposition. So I can just do the math and argue that there's going to be less than one bad edge on any particular path with high probability. So if there's less than one bad edge, that means that the path I'm trying to argue has been shortcutted is entirely in the black subgraph, which means we're already done. So I don't even do anything extra for the red edges. We're just going to be finished.
One question. So I guess little d is that?
Yeah, sorry, I don't think I highlighted that. So little d is the parameter to the low diameter decomposition.
No. Do you set that to? When you have set that there to?
Yeah, it's got to be a lot of log factors to make it so it's more than the log squared.
D, right?
Yeah.
So it's more than d. It's not just it's theta of d.
So it's got to be more than d times log cubed.
More than capital D times log cubed.
Yeah, to make it
We're
work.
getting the diameter bound on each of these components with high probability.
Yes. So with some probability, the low diameter decomposition doesn't give you the guarantees that it's supposed to give you, but you're going to repeat this algorithm a few times. So this is basically their algorithm, the 2-slide version. I'm sure if you want to hear more about it, you can go to their talk at SOSA. OK, so back to reachability. So the general structure of a parallel reachability algorithm is we need an algorithm that can solve the hop-limited version of the problem. We have that. That's parallel BFS, limited to some number of hops. We use that algorithm to build a shortcutting algorithm. But now we only have to worry about shallow graphs. So you kind of generally don't even have to worry about parallelism at this point, because the only tool we're using is this, which is already parallel. From here, we can apply that reduction from the previous slide that says if we can do shallow graphs, we can do general graphs. And then once we have the graph is low diameter, we can just solve reachability using the hop-limited reachability algorithm.
So all the algorithms that you presented, they're all Monte Carlo one.
They're all Monte Carlo algorithms.
So in principle, can you verify that the result is correct, or?
I don't know how to verify that they gave you the diameter efficiently. You could do it inefficiently by just, but if we're trying to solve the reachability problem, we do get a Las Vegas algorithm for reachability, because if this runs too long, your diameter reduction didn't work. So you just do that again. So this is Monte Carlo, this is Las Vegas. Okay, and so really the only hard part is doing the shortcutting for shallow graphs at this point. Everything else we have the pieces for, or black box reductions. Okay, so I want to give you an idea of the Jumblapati, Liu, and Sidford improvement. So this was my algorithm again. All they do is they choose more than one pivot, and then you search forward and backwards from each pivot that you chose. And you partition the graph in the way you would expect. So something like that would be the result I get for this example. There would be too many shortcuts for me to draw in the slide, so I'm not drawing the shortcuts here. But this will then split the graph into a lot of pieces. Like I have this piece here where these two searches overlap, this piece here where these two searches overlap, this piece here where there's only that one search hits it, and so on. Okay, so that's the change you need to do. And the way they choose pivots is by having some tuning parameter k, which will be polylog n. And they sample vertices with increasing probability as you recurse. So it's something like k to the d over n. So at the top level of recursion, you're only sampling about k pivots. When you get down log base k of n levels of recursion, everybody is sampled. So that's the improved algorithm, basically the same thing. And I think I will tell you roughly how this works. So bounding the work is actually pretty easy, and I'm going to sort of skip this. But it's pretty easy to argue, you could probably do this as an exercise yourself, that at recursion depth d, each node is related to at most n over k to the d nodes in its subproblem. Okay. The only trick you would need to do is, yeah, I won't go into that. You can figure it out for yourself, or I can tell you afterwards. So once you have this, how many graph search, or what's the total cost of the graph searches you're doing at depth d? Well, each vertex is visited by, well, let's see. So this is the number of vertices that are related to it. This is the probability that one of those related vertices is chosen as pivot. So this is the number of pivots that end up searching to that vertex. So each vertex is not visited by very many of the graph searches, which means that the overall running time is going to be linear times k, which is linear if k is like a polylog. Okay. So that's the idea there. You have to do some details to manage these now we have concurrent graph searches and stuff, so you have to be a little careful about how you're doing those. Not hard to do when you don't care about log factors. Okay. They can also argue now if you, now an issue here, or maybe advantage or disadvantage, it's sort of hard to tell, is that we're going to select a lot of pivots at once. So we could end up chopping our path into a lot of pieces in a single round of the algorithm. And they're able to argue a generalization of that knockout argument I gave before, which says that if we happen to choose tau pivots that are related to the path, then on average, the number of ancestors and descendants in total goes down by a 2 over tau factor. Okay, so that's all this says here. So if we plug in tau equals 1, this is actually no improvement is what this says, but my analysis would have been better in that case. If tau is strictly bigger than 1, then you do better here. Now the problem is we don't always know that how many pivots you're going to get that happen to be related to the path, so it's kind of hard to argue that this works in general. But let me give you a hand-wavy idea. So let's imagine that we started with the path, and I'm just going to fix a particular number of vertices that are related to the path. This number I'm choosing because it's going to work inductively. I'm just going to do a hand wavy. Let's assume the average thing happens. So I'm selecting pivots with this probability, which means the number of pivots I'm going to select is this many that are related to the path. So in total, R is going to reduce by that much. And those are going to be split across that many subproblems. So if I look at so I'm going to select a bunch of pivots, I'm going to chop the path up, it's going to induce a bunch of subproblems. And if you do the math out, you'll see that each of these subproblems has a 1/k factor fewer related nodes than the one above. So I'm in the same situation again, and you can argue the same thing again. So at each level of recursion, the number of subproblems is growing by square root of 2 to the k. The recursion depth is at most log kn, because at that point you're selecting everybody as a pivot. So that means that they're at most square root of 2 to the k, or square root of 2k to the log base k of n, or n to the 1/2 plus little o of 1 subproblems. The subproblems are the things that will not be shortcutted, or sorry, that will be shortcutted by the time we're finished. So the only edges we're concerned about, the final path length, is just the edges that cross from one subproblem to another, which is that. So there's roughly square root of n path length in the end. Okay, so that's sort of the quick summary of how that works, but probably not enough detail to really get it. All right, so let me just summarize what we have for reachability. If I'm interested in hitting a span that's something like square root of n, this is the work required to do it with various algorithms. One algorithm I'm not talking about is Van de Brand and Galizade, Zhang, and Vos in SPA this past year showed an algorithm for min-cost flow that they could make parallel. This does have an n to the 3/2 work cost in it, so it's not linear work in total. But you can use this to solve reachability as well. I'm not covering that approach in this talk. And then on the bottom here, there's a bunch of algorithms with work span trade-offs, where we get to tune some parameter to adjust things. And this algorithm at the bottom here with Nairen is really just a work span trade-off of the JLS algorithm. The overheads here look like they're worse than the overheads of the Spencer and Ullman-Yanikakis algorithms, but they're not, because we're starting with a better baseline. So you should kind of relate these as like rho squared here is kind of similar to rho up here. Yeah.
One of the things you did about Spencer's algorithm is good because it's randomization.
Yeah. Yeah, I don't know of any unrandomized versions of any of the algorithms other than Spencer's here. Yes, sir. All right, yeah, so there's a work span trade-off for the JLS style algorithm as well. Okay, you can also solve topological sort and strongly connected components using reachability as a black box. So there's a couple of solutions that do that. These are all based on the divide and conquer algorithm of Coppersmith, Fleischer, Hendrickson, and Pinar. So you get the work and span that you would get for the best reachability algorithm. There's also a deterministic extension of Spencer's algorithm to SCCs this last year at SPA, which gets Spencer-like work and span, and it does so. I actually don't remember the details. These guys had a deterministic algorithm as well, so I imagine that they adapted the deterministic algorithm of that and mixed it with Spencer's algorithm, but I don't remember for sure. All right, so that's all I want to cover for reachability in the last sort of 10 minutes-ish. I'm going to try to cover single source shortest paths very quickly. Okay, so what do we know? What's really easy to do? If I have an unweighted graph, I can find h-hop distances using parallel BFS in linear work and h-span, right? This is just cut off the breadth first search after h-hops. So these are the h-hop distances I'm drawing up here. We don't know how far away the things that are more than h-hops away are, but we got the right distances to everybody that's less. Okay, maybe a little bit less obvious, but also not hard, is if we're talking about strictly positive integer weights, we can find shortest path distances at most d, so not d hops, a distance of at most d, in M work and D span. And you can conceptually, you can just think about this as treating each edge with long length as multiple unit weight edges. But that implementation won't be efficient. So most people kind of view this as like a bucketed Dijkstra's algorithm. But it's not hard to do this in linear work, roughly linear work. And in weighted graphs, we can find h-hop distances using Bellman-Ford. Bellman-Ford would need to run h rounds of relaxing all the edges. So this would be mh work and h-span. Okay, so those are the easy things that we have as building blocks. Now, I'm only going to be talking about non-negative integer weights here. Nairan had a nice result for negative integer weights. But this is all I'm going to be focusing on. OK, so if we look at the Ullmann-Yanikakis algorithm, this actually works well for the unweighted case if we just change it a little bit. So what we're going to do is we're going to sample square root of n vertices, run parallel breadth first search from each sample, limited to square root of n hops. So far the same algorithm. And we're going to add shortcuts between the samples in the same way. But now we're going to put a weight on the shortcuts. And the weight will be equal to the breadth first search distance. So we're going to add those shortcut edges and put some weights on them. Okay, so that would be what we get. And then we'll just add one step at the end. Oh, sorry, I'll say that was the work and span for Ullmann-Yanikakis. It's already really high, right? Really high work. So now we can afford to run Bellman-Ford, limited to square root of n hops, which is going to have the same work and span. OK, so thinking about this again, right, we have the same argument on the path length, except now we're thinking about a shortest path. We now have weighted edges, so we have to run Bellman-Ford instead of breadth first search. But we only have square root of n hops along the path, so we're good. OK, so they do that in their paper, and they solve unweighted shortest paths. OK, so again, their strategy is add weighted shortcuts with the goal of making it so for any pair of related vertices, there is now an h-hop path with weight that is equal to the distance. And then you can just run h-hop Bellman-Ford. The main issue with this is the work is really high. And the fact that we're running breadth first search to add the weighted shortcuts means that this does not obviously generalize to weighted graphs. We can only do it for unweighted graphs. Okay, but we can relax this a little bit. So rather than getting exact distances, we're going to try to make it so there's now an h-hop path from u to v, where the weight of the path is at most 1 plus epsilon times the distance, and get this sort of approximate distance shortcutting. And then we can run h-hop approximate shortest paths. Turns out you can do h-hop approximate shortest paths in linear work and h-span, which I probably will not have time to talk about. Yeah, so this view on the right is what's called a hop set. So if you've heard the term hop set come into play, it is just the approximate version of what we just did. So epsilon is controlling this approximation factor. H is called the hop bound, is controlling how many hops we're allowed to have on the path. That is approximating the shortest path. OK, so the general structure of an approximate single source shortest paths algorithm is pretty much the same as the general structure for a reachability algorithm. We need some algorithm that solves the hop limited approximate problem. We're going to use that to build hop sets. We only need to worry about an algorithm that builds hop sets on shallow graphs, because very nicely, they also solve that reduction for the hop set problem. That will give us a hop set for general graphs. And once we have a hop set and hop limited approximate shortest paths, we can solve approximate shortest paths. The hard part is constructing this hop set.
And this is for weighted graphs.
This is for, well, yeah, so we're going to try to make this work for weighted graphs. But yeah, this is for whichever regime you're in, it's still the same strategy. OK. So what are there good hopset algorithms? Again, I'm only focusing on the algorithms that use a linear number of shortcuts. And I've already shown you that you can make Ullmann-Yanikakis give you a hop bound to square root of n with m times square root of n work, but it only works for unweighted graphs, although it does give you exact distances. So we have an exact hopset in this case. Klein and Subramanian showed how to extend the Ullmann-Yanikakis algorithm to weighted graphs. It gets pretty much the same complexity. But it's now an approximate shortest path algorithm. And then with Nairan, we showed that you can extend the JLS algorithm to build hopsets as well. OK, so the idea when extending the JLS algorithm to do hopsets is you're going to add weighted shortcuts, so you're going to use approximate shortest paths rather than a graph search to find all the vertices and stuff. So that part's sort of very natural. The issue is that if we look at an example here where I selected as pivot a bridge, so it's something that can be reached by the start of the path and can reach the end of the path, this was a case we wanted to argue made us done. But if this bridge happens to not actually be on a path that approximates the shortest path, so this bridge is on a path that has length 52, and the shortest path has length 7 here. So this path is not a good approximation of the actual shortest path. This bridge is actually not good. We're going to end up partitioning the path into a bunch of pieces, and we can no longer argue that we're done. So we had to somehow get around this case, which was sort of the problem. And we have ways of doing that, but I'm not going to cover that here. But that's a challenging aspect. All right. Yeah, so I think I'll skip this unless we have extra time at the end. So Klein and Subramanian also showed how to do hop-limited approximate shortest paths. It's basically just a simple trick where you scale down all the edge weights to small integers, and then you scale them up. You lose something in the rounding process. But if you choose the right granularity to do the scaling, that is somehow proportional to the actual distance of the path, this does a pretty good approximation. And you can do it in linear time, or sorry, linear work and roughly order h span. OK, now it turns out that if you can solve approximate shortest paths, you can also solve non-negative integer shortest paths through some other reductions using scaling. So Klein and Subramanian actually did this in their paper as well. They showed how to go from approximate, or to use their approximate single source paths algorithm to produce an algorithm that's an exact algorithm for non-negative integer weights. But their reduction was kind of expensive. Nairan and I showed that you can do a reduction from hop sets to exact non-integer shortest paths. And then in the same year, that long list of authors showed that you don't need hop sets explicitly. You can do a reduction from approximate single source shortest paths to exact non-negative. And these just do some scaling type of approach. There are some challenges there which I won't cover, but that's roughly all there is to it. So they get a, running time will depend on how big the weights are, because you get something that's logarithmic in the maximum weight. Okay, so that's pretty much the state of the world at this point. If we want to do better algorithms, we would need better hopset algorithms or better reachability algorithms. But I believe that's the end. Yep, OK, good. I got to the end. That's the end of my talk.
Time for questions?
Yeah.
Sorry, I missed most of the talk, but when you're putting in shortcuts, there's this lower bound on edge addition of shortcuts, which maybe you mentioned, right?
Yes, I did, yeah.
So what happens if you want to add vertices?
Yeah, so the question is what happens if we're adding vertices in addition to adding edges? I don't think there are lower bounds that are known, and it's also not clear how that helps you. It's an interesting question. We don't know how to use it.
if you want to beat the lower bound, if you wanted to get to polylog, you would have to do something like that or something completely different.
Yes, and there's also still a gap between the upper bounds and the lower bounds, and we don't know how to do the lowest diameter shortcutting in parallel or efficiently, so there's some open questions there. Yeah.
So do you know if anyone's tried implementing any of these algorithms? Like, do we have some hope of actually realizing these things, these improvements practically?
Yeah, so the question is if these have been implemented and if they're practical, and as far as I know, no one has implemented them. I think if you do exactly the way they're described, it would be quite kludgy to actually put these things together. The constants are terrible. But if you just try to do roughly the spirit of the algorithms, I have no idea. I would think they work okay. The problem is I don't know how many real graphs fit into the situations where you would need something like this, because in practice, parallel breadth first search often works kind of okay, right? So we need a graph that's like sort of sparse, which would usually have low diameter, but also has some long diameter piece to it that somehow you can't just discover and do something else with.
Or like the scaling algorithms that you were mentioning, right?
Yeah.
Anyway.
Oh, so have the scaling algorithms been implemented?
For approximate SSB, there's also these kind of...
So not for the parallel version, but I don't know. Have you seen some of those scaling algorithms, like Gabo's algorithms, implemented for shortest paths? Or?
I've done something, because the scaling, when you implement scaling, you wind up enforcing a lower bound, right? Basically,
yes.
like, because now you have to do these log iterations. I mean, so I've done this for things like matching or max flow, so it's almost always worse because, really we generally have good ways to solve the problem without scaling. You put this lower bound of log, the biggest number, which is 20. You just put a factor of 20 in or something, and that tends to slow things down when you have a non-scaling version available.
Yeah.
It's also one of the challenges it's a top min-cost flow because you sort of have to scale there, and that's why min-cost flow seems to be a lot slower.
Yeah.
Can you give some flavor of what those graph constructions were like earlier in the talk?
Ooh, I don't remember all of them, but basically they end up, so the question is what are the graph constructions like for the lower bounds? They end up building graphs that have a bunch of layers where all edges go from between consecutive layers, so it's sort of easy to argue about the types of paths you have. I think they try to construct it so there's sort of only one path between certain pairs of vertices, but that they don't overlap too much, and I can't remember exactly how they do it. But,
You mentioned that there is in terms of that question, there is a gap between the upper and lower bounds. Maybe it's implicit in your talk, but I was wondering, can you describe what kind of a gap that is? So
yeah, so the best upper bound for shortcutting, so this is, we don't care about computation.
yeah.
If we want to get the diameter as low as possible, but we don't want to use too many shortcuts, you can use roughly linear and n shortcuts and get the diameter down to n to the 1/3. The lower bound for the roughly n shortcut regime is n to the 1/4. So we have a gap between n to the 1/3 and n to the 1/4. We also don't know how to do the n to the 1/3 shortcutting efficiently. And there's a component of their algorithm, of Kogan-Parter algorithm, that if you want to implement exactly that component will require m times n to the 1/3 work, but it's not clear you have to do that. So
most of the algorithm, it is related with randomness. So does it require the graph also be random, or it may fail on some ugly graph like the shortest path example?
So the question is, a lot of the algorithms are random. Do we need random graphs for things to work well? No, so all the randomness is just in the choices of pivots we're making. If the graph is random, then you can do other things that are better.
Just to follow up on Bob's question, could you even think of something more radical? Like, you could think of destroying part of the graph and rebuilding it in such a way that you will preserve or approximately preserve. Sure. In undirected graphs, there are things like low hop emulators. There are things like that.
Right.
At a high level, do that. So, any of those ideas?
Yeah. So the question is if there's other graph objects like emulators that are useful here. I don't know. I haven't seen those being used.
There is
I don't know how to do them.
on the Go you work, I think. they show a lower bound if you only add order n edge with emulator, you still have a lower bound, polynomial lower bound. But it's unclear if you add order m edge. So the conjecture, you can get some polylog depth, and then it's just a conjecture.
Okay.
This is in directed graphs?
Directed graph.
Yossi, was that the same question?
Yeah, I mean, can you clarify Monte Carlo versus Las Vegas for the shortest path? Because you only
Yeah, so,
clarify for distributed.
so the question is Las Vegas versus Monte Carlo for the shortest paths. It's the same deal. So
Same thing.
we have Monte Carlo for generating the hop set, but the actual shortest paths we'll know if we got the right answer quickly or not. So we get Las Vegas for the shortest paths. Yeah, actually.
So it seems like we're converging to like these root n style bounds for all these directed reachability style problems and the shortest path problems. Are there any like outstanding kind of examples or problems in this family that we haven't gotten that bound for yet?
So the question is, it seems like we're converging to root n type bounds. Are there other problems where we haven't gotten these same bounds? Yeah, the only problems I know that we've really explored as fully are these two easiest ones. So reachability and shortest paths, and then the things you can solve with reachability or shortest paths. I don't know what the state of the art is for things like flow, which gets a bit tricky, because then you tend to not want to use these combinatorial algorithms anymore. You tend to want to do something else. That also had root n as the bound for the best parallel flow algorithm, but the work is worse than the best sequential flow algorithm. I think they got that because they are, it is not because they're doing the same kind of shortcutting thing, it's because they're doing some sort of iterative gradient descent, interior point, whatever type of approach, and the algorithm just happens to need that many iterations. So that square root of n is kind of coincidence. So I don't know for more sophisticated problems. Maybe Nairan has looked at some others, but I've mostly only seen as far as shortest paths.
Any other questions? All right, thank you very much. We'll resume at 10:45. I'm confident there's coffee.